So this relationship is going to be non-linear. Here if I plot omega versus k, this is simply this your slope is v, right? So this v is called actually group velocity. Because this is, we are talking about summation of this superposition of waves, right? Everybody familiar with this group velocity versus phase velocity? So if you have like several waves with different frequencies, if you add these things, what you are going to get is some kind of envelope, right? So the envelope is actually moving with the velocity of group velocity. Then each of these things are moving with velocity of, we call it phase velocity. So here we are talking about actually this v is the group velocity. So now if I assume my material to be elastic continuum, so I define simply the group velocity given by this omega equals k times your group velocity. Sometimes we can say it is Vg. Please remember that one. V is the group velocity. Typically we call this is dispersion loss, because later we are going to show this omega is something like 2c over m sine squared k omega over 2, sorry, k over 2. You can see now this is not linear, right? Omega and k, they have more complicated. That's a dispersion relationship. But right now, your dispersion is simply this simple one. That is the for the continuum medium. Now we will use this one when we use the ideally Vg is defined as d omega over dk in a more complicated way. Then phase velocity usually defined as omega over k. So in this case, d omega over dk is same as this one, right? In this case, your group velocity and phase velocity are the same. So this ideally, this is the relationship. So we are just going to talk about. Okay, now let's talk about. I said now we know one thing. Because what we are going to do is this. We are going to calculate n omega, right? But we don't directly calculate n omega. What are we going to do? Calculate n k. So then when we know k, we can calculate d omega over dk. But in this case it's easy, right? What is d omega over dk? Simply Vg, right? But in later it becomes more complicated. But in our case, in elastic medium approximation, omega is Vg times k. That means, suppose this is has k dependence, so d omega is n omega is nk dk over d omega, right? So that you can easily get d omega over dk is simply Vg. So that's so simple, okay? So that's the approach. So what the only thing we need to know is how to calculate this nk. How do we do that? So to do this one, so you can do it in, so this number of, please read this one. Vibrational mode is associated with some k, right? Because each atom is vibrating with this frequency omega, so omega is related to k. That means you can represent this one as a wave. That's what we call phonons, right? So now we are going to calculate how many these modes are there for a given energy range, or maybe delta k or delta omega, any of this range. How many modes are there? So that means if the modes are say dn, so that you can write as that n omega times d omega, or ne times de, or k times dk. Actually, that's depending on your dimensionality of k. So I will show how to do that. So that is the thing, right? Between omega and omega plus d omega, that means d omega range, right? E and E plus dE means dE range, here delta k range. So I will give you very general expression to calculate for any dimension. So everybody understand what I'm trying to say here? So now, how do you calculate this nk? So to do this one, we need to create some space. We call this a k space. So it can be kx, ky, kc. We have to find solutions for this waves in this k space to represent each mode. So in 3 dimension, then this is if you have some homogeneous one, it's a sphere, right? In 2 dimension, it is basically circle, right? In 1 dimension, it is basically line. So these are the each mode. So what you want to find is how many modes are there between these two for a given delta k. So I have delta k. Suppose this is my delta k. How many modes are there? Okay, that's what you need to calculate. First thing is to get what are these k values. So this is what we are going to do. Is very simple. What we are going to do is use some simple boundary value problem. So suppose if I have a linear chain of atoms like this. Suppose I have these atoms here. Suppose this is S atom. This is after n, you have S plus n atom, right? So if the separation between each one is A, that's a lattice constant. So then this length is L times Na. Suppose that is your length of your crystal. So that means this is basically total length, right? N times A. So now what I'm going to do is, I'm going to bend this one into a circle so that this point and this point will be coincident. So if I do that one, so that's how you get the boundary value. If I bend this one, you can see this is the S atom, this one. Now when I bend, so this is S plus 1, this is S plus n minus 1, this is S plus n, right? So that will coincide with S equals A. So then you can get the series of these k values. How? So if you write the solution for this wave, if I write u as, so typically they have harmonic function, right? Solution you can write as some e, I, k, x kind of solution, right? So these are the standard solution for the harmonic oscillation. Then when, if you want, you can put omega t terms, but we only consider x dimension, right? So then you can see when x equals s, that u value is same as x equals s plus n, right? So they both have the same u. So then if you write that one, very simple. So if I write this one, that's the solution, right? If I write s and s plus n, is that clear? The u is basically I, k. Now x is what? For the s atom, x is s times a. So for the n plus 1 atom, x becomes s plus n times a, right? That's it. So if you put that one, you can say here k s a, k is there, here k s plus n, right? Omega t is there, a omega t cancel. Then what do you get here? If you do that one, you get e I k s a, omega cancel, right? K s equals e I k s a plus K N A, right? That's it. So then you can say K cancel, then you get E I K N A equals 1, right? Is that clear? So now you can see how do you get 1 for exponential term? Anything that has EI integer 2 pi times n, right? So now you can see I can get K values as 2 pi over NA. NA is actually L, right? So times your n. So for each n I can represent it some n. You can see you can have like 2 pi over L, 2 times 2 pi over L, 3 times 2 pi over L. From every direction you can get each point. The separation between each point is, so if I write this one at the position say 2 pi over L, next one is say 2 pi over L times 2, right, like that. So but the difference between 2 is basically 2 pi over L. N point, and what is next one? K n plus 1 point is basically 2 pi over L times n plus 1, right? What's the difference between these two? 2 pi over L. So that's how we get the boundary value condition to create the K space. So later we'll do the similar thing if you do for electrons and things like that. So here this is what I'm going to say. So you get 2 pi n over n is, I just wrote L is basically n times A. So if you do this one, you create this K values, right? Each K value is a solution for this wave equation. So now we have K space. Only thing now we have to calculate is what is the, how many states are there for a given delta K. That's very simple. Is that clear for you? So K value. So if you calculate now, like I said, the difference between these two is delta K, right? Delta K is 2 pi over L. The separation between allowed solutions in K value is simply 2 pi over A. So that means how many modes are there for a given delta K? That is 1 over K, right? 1 over delta K. So that means you can say your number of modes for unit delta K. That means, because here we are talking about 1 mode here, right? So the 1 over delta K, that means L over 2 pi. That's this very important thing to remember. So number of modes for a given for a unit K, right, is L over 2 pi. So L is the length of the crystal. Now if you have 3 dimension, what do you get? You get L over 2 pi in all 3 directions, right? Then you have L over 2 pi times L over 2 pi times L over 2 pi. If it is a 2 dimensional, it's only this much. So that here, this is what I was. So this is the number of modes per delta K, right? So you can see this is, if you do this one, what you get? L times L means V, right? Over 8 pi Q. Okay. So now if I know my dn, we said it is, you can write either way, right? So now we know nk. What is nk? This is the really nk, that is the number of modes per unit delta K. So that means I can write this nk as, that means dn is basically v over 8 pi cube times this d cube. If it is 2 dimension, what do you have? So then this becomes dn equals a over 4 pi squared, right? A over 4 pi squared. Then you have d squared k. That's simple, right? If it is a 1 dimensional case,
L over 2 pi.
yeah, this is L over 2 pi times your just decay. That's it, very simple. So if you do methodically, you will never make a mistake. So here, this is for the three-dimensional case. This is dn is basically V over 8 by Q terms. This is clear, right? So this is the number of modes per that unit is a delta K here, right? Now whole idea is how do you do it for some known volume. So we'll do that one. Is that clear so far? So, yeah. So now what is this dq k if you want to do for an entire sphere? So this will be, you have to, in three-dimensional, this is more like you have a total sphere, right? So that means you have the area, volume means area times your dk, right? Because eventually we need to get d omega over dk. D omega over dk. So that means if it is a three-dimensional case, you have area in k space times dk. If it is a two-dimensional case, you have perimeter times dk, right? So you have to, yeah, I'll do it in more simple way. So because this d cube k, so here d cube k means volume. Volume is a sphere multiplied by something like this. In three dimension I have k. So if it is a homogeneous one, this is really, what is that area? 4 pi k squared, right? It becomes 4 pi k squared times dk. If it is a two-dimensional case, what do you get? You have 2 pi k times dk, right? That's the particle density, right? Number of particles per unit volume. You can write as either omega max as Vg times 6 pi squared simple n. Typically we write 1 over there. Simple n means capital N divided by V. Okay, so that's it, right? Now you can easily write your expression for this one. So if you remember here, okay, let me get what is the expression we knew for Einstein model. Here, CE, if you remember, that is, what do you remember? That CE was this one, right? This. That is the complete expression, right? So then, everybody familiar with this limits? Everybody fine, right? So if I use that one now, everything I have to do is what? Here. This one, n omega is now this some constant time omega squared, right? In omega. So this one has all these functions like constant, then you have theta e over t, then you have e theta e over t divided by this exponential minus 1 squared. That's it, right? So then we have d omega. So now if you substitute this one, you will see this theta e is nothing but, yeah, this important thing to remember. Theta e is actually a temperature, that is h cross omega over kb. This theta e. So that is for any general, because this has a function of without temperature, right? So then theta maximum, when this is h cross omega, remember we had omega maximum. This one is defined as theta d by temperature, because we introduced a maximum, right? That's the cutoff frequency. So please remember this one. I'm going to give this problem for you to work for two-dimensional case, then you will understand. So if you do this one, you will see, you get all these things because in this expression you have omega squared now extra, right? Omega squared. So then we get here you get the same thing coming from this expression. That's what we have, the same expression. If you manipulate, you get the same thing. So because this is coming from the Einstein relationship, right? That is for 1. Now we just integrate over omega squared. So the EC also there, the same E. C is here. So then this is theta over E squared, right? Yeah, this one also squared. So this one has omega, right? Because theta E has omega. That you get omega squared, right? Omega squared and new omega squared coming from n omega, that becomes omega 4. See, I have omega squared coming from this one, then I had the omega squared coming from n omega, right? That makes it omega. You can easily. Okay. So, but if you want to derive this one from the from beginning, I even put together like this. So is this clear for everybody? That is n omega, right? So this is also fine for everybody. So integrate, you get n. So now if you want to calculate total energy is what? Total energy is, this is very important. If you have one oscillator, what is the average energy of that oscillator? We know it can be filled to some state h cross omega, right? N h cross omega. But what is the average energy of that oscillator? That we calculated using that Boltzmann distribution function, right? Remember E minus beta E, that is h cross omega n. So then when you divide by the total, this one you get the average value, right? So if you do that one, that average value everybody should remember, that's the average energy, h cross omega over this one. Remember this one came from that summation thing, right? Please remember, for one oscillator, average energy is, average energy of oscillator, this is one, average energy of an oscillator is given by h cross omega divided by E h cross omega over kBt minus 1. Please remember this one, this is very important. So that means this is the average energy oscillator. Do you have how many oscillators in that d omega range? This is the density of state, right? Then if you integrate over d omega, you get the total energy. That we did initially even for the first one. So that's it. So then you make some kind of these substitutions. If you follow that one, so that is U, right? So then CV you have to differentiate it. We did this one before. If you do that one, you get this final answer. Or you don't have to do anything, just start from that solution, from the Einstein solution, and put it in the integral, same thing. But when I give the homework problem for two-dimensional case, you have to follow this way. But what's the only difference? This will be different, right? Two-dimensional case. Then you have to get different value here. Other than that, everything is the same. Everybody should do this one, otherwise you will never learn. Okay, so now we calculated the heat capacity for Debye formalism, right? So now this is also pretty complicated expression. So I will look at both high energy and high temperature and low temperature. If I go to low temperature, that means please remember this theta d is the Debye temperature. This is very important thing. If you look at materials, This Debye temperature will tell you how stiff your material is. The Debye temperature measure of your stiffness. For example, if you take diamond has very large Debye temperature. If you take a soft material, that has very low, because that tells you your stiffness of your material, right? Heat at this Debye temperature, this is given by H cross omega d over Kb. What is omega d? That's the Debye, that cutoff frequency. So now if I look at low temperature, the high, first let's look at the high temperature. That means T is much greater than the Debye temperature. In this case, your C is defined as, C is basically H cross omega over kBT. So your T is much greater means your C is very small, right? Because T is in the denominator. That means you can assume your C is going to 0, then EC becomes 1 plus C, right? So then if you plug in here in that expression 9K, this one, then you get that here EC minus 1 is basically C, right? C squared. You can see EC also becomes very small 1. So if you do this one, do that integral, you get 3R. It's pretty good, right? That's what we expect. High temperature, your value is, remember our CV high temperature is 3R value, right? So that's pretty close. But low temperature, now let's see how this one. If low temperature means my T is much lower than theta T, right? So then only difference is, this is the typical integral if your limits are finite. So in that case I can make my C maximum infinite because C is very large, right? So if you replace that one, this is integral to 0 to infinity. At least you can do this one by Mathematica or MATLAB. If you do this one, you will find this like 4,15. So you can easily get this a finite integral. Plug in this one here, 9K, this one. So if you plug in, you get 12 over 5, because you're 5, 3, 12, you get this answer. What is that? This CV is directly proportional to TQ. This is a very important expression. If you are studying some material, the phononic contribution for your heat capacity at low temperature goes like temperature to the power 3. This is really important thing to remember. So later we are going to talk about electronic contribution. This is just the phonon contribution. If you take diamond, low temperature diamond heat capacity goes like T to the power 3. Now if you check this one with your experimental results, see how good now. These are the experimental results. This is the new Debye theory. So that's perfect, right? Previously Einstein one was good here, but here that dropped a little faster. But Debye model, it was really good. Debye model is more successful than Einstein. Here are some of the ones I said, the theta, the Debye temperature. So you can look at some of like diamond. If you take that, Debye temperature is very high. For soft material like lithium, sodium, they are much smaller. Even like lead, that also soft metal type. So, so lithium fluoride, these are a little bit stiff material. They have much higher Debye temperature. Debye temperature has a meaning, right? Yeah.
So like what happens to the material when it reaches that Debye temperature? Does it just break apart?
No, because that tells you how difficult for it to vibrate, right?
Okay, okay.
This is all coming from the phonemes, the vibrations. Okay. Yeah, so this is also, they plotted that times t cube. So, because CV is going like t cube, right? Previously they plotted dash t, right? That's why that. But if you plot like t cube, your x-axis then is perfect straight line. Okay, I think that's what I want to talk about before we go to, so little bit more. So because previous assumption was your crystal was simply elastic medium, right? There are no atoms in the solid. Now what we are going to do is basically introduce atoms in your solid and see how these are vibrating. So first we are going to talk about this one-dimensional monatomy. That means you have same mass atom here, like they all have mass m. So next I am going to introduce like two atom bases, two different atoms. So then you have different characteristics. So just imagine this m, mass m, all these atoms with lattice constant A. So I call this one S atom, S minus 1, S plus 1, S plus P. So now they all are attached by springs. That's the model, right? So you can, because these are vibrating. So I can represent each atom by springs, right? So suppose its spring constant is some C. So now just concentrate on particles. So this is at equilibrium. So at some time, so each atom will vibrate to a new position. Suppose from here, this is moving by US minus. This is S minus 1 atom. They move by S minus 1 distance. This S atom moves by US. S plus 1 moves by S plus 1. S plus P atom moves by S plus P. Right? So now I am going to calculate what is the total force on this S atom due to all the effect from all the atoms. So, but later I am going to approximate only considering the two nearest neighbors. So if I consider all the atoms, can I write the total force? So let's see, so if the force constant is C, suppose Cp. So they all are the same, right? C. We can assume all the force constant, the spring constant to be C. So then if I consider this S atom, what is the total force on this one? Because this here, this atom is moving by US, but if I consider this one, this is moving by US plus 1. So then what is the total displacement? The US plus 1 minus US, right? So that means I can write the total force as force constant times for the pth atom. So I can say US plus P minus US, right? For the pth atom. But it can be say first atom from S plus 1. That is, so then from the next one I get US plus 2 minus US, right? So, but also you have other side also. P can be negative also, right? So this one, like, I can write this one as total as sigma C. I assume they all have the same P eventually. What I have is US plus P minus US. So that is my total force. So this should be equal to mass of that S atom, m d squared US divided by dt squared, right? That's the Newton's second law. So this is for the S atom, but this is the effect on this S atom from all the atoms. So is this clear for everyone? So this, if it is only nearest neighbor, P is 1, plus or minus, right? You have in both sides. If it is second, it is plus or minus 2. So this is for in general situation. So actually this is not difficult to do. So how do you solve this one? If I write my solution, you can see how that one, this is how it's going to oscillate, right? Between your equilibrium position. So this is how you write the equation, right? mv squared over dp squared cp, this one. So how do you solve this one? We have to assume solution for us, right? So it's typically we use harmonic solution. Us has some exponential eik. This is the solution. For the S term solution is some amplitude ei kxs minus omega t. K, what is xs means? S datum, so that's distance is if you have some origin, S times A. So now just take the derivative of this one. You have to take derivative twice, right? You take first derivative, you get minus I omega. If you take the second derivative, again minus I omega, then you get omega squared, right? So that's it. So then if you write that one, here, minus I omega squared, yeah, that one. So then here also I have to plus, what is us plus p? K, that this is s, x, s plus, the s plus p, right? S means, xs means a times s, x plus, s plus p means a times s plus p, right? Okay. So we just put here that is s plus p. S is same to this one, right? You can see omega t term cancel. What you are getting is this one. Yeah. KSA also I can take out, right? KSA, KSA, KSA also comes out. They cancel each other. So then what you are getting is simply, I think everybody can follow this one, right? So that's the final answer. Minus n squared. These two cancel. Yes. That's easy, right? So this is the general expression, effect from all the atoms. But here you have atoms from both left and right. Now, if I want to only consider to the right, what do I do? But here P is for both positive and negative, right? I can make only positive by adding P minus term into this one, right? So that means I can make, here P means all P. P can be negative or positive. I will put P only positive by putting another term that has P equals negative P, right? That means I have something like Cp EIKPA minus 1. Then if I put plus, I have EIK minus P, right? Minus P A minus 1. So you get minus 2 here, right? So if you do that one, this P becomes only positive. Because now I have already included negative term into that one. So then what you get is simply this one. About paper 2 right here. So if you do this one, P is only now positive. You don't have to consider negative term. Okay, so now what is this one? Ex plus E minus x means 2 times cosine, right? Even cosine x is basically E Ix plus E minus Ix divided by 2, right? That's what take up 2. This is plus KPA. Then, yeah, so I put 2 out. So then I have this 2. Okay, so that is general situation considering all the atoms. But for simple consideration, we only consider only nearest neighbors. Nearest neighbors means P is only 1, right? You don't have to consider left one, we already considered that one, right? So then your answer is minus m omega squared is simply 2cp cosine P is simply 1, right? Cosine PA minus 1. So only the nearest neighbor, if you consider only the, yeah. So here I just wrote 1 minus cos means 2 sine squared half, right? Remember this one, cosine 2x is 1 minus 2 sine squared x. So that means that cosine 1 minus cosine 2x means 2 sine squared half of this one, right? So that's why you get half. Simple. You should remember this one. So then if I consider only the nearest neighbor, that's the answer. Omega squared is 4c1 divided by mass sine squared this one. That means omega is square root of 4c1 over m sine of Ka, right? This one is the positive value. So this is not like omega equals kVg, right? This is different dispersion. So if you plot this one, actually what you are getting is like this sine, right? But we are only plotting up to this. If you remember your brilliant zones, anybody remember that? This is still K space, right? So this is actually pi over A, this is minus pi over A. You can see here, this is actually similar to that elastic medium, right? So these are still, so actually we call these modes as acoustics modes. That means these are low frequency modes. Low frequency means, low frequency and also low K value, that means high wavelength. So these are acoustic phonons. So that's what you have to know, like if you have some light interacting with these phonons. So anybody know the name for light interaction with this, the acoustic phonons? These are called the Brillouin scattering. Probably you all know. Later we are going to talk about high frequency modes. So they are called optical modes. So anybody knows what is interaction of light with optical modes? That you all have done, but you don't remember. That's the Raman scattering. Raman scattering, you have these optical phonons, so they interact with the light. Here we are talking about this. If you have these monoatomic ones, they don't have optical modes. They only have acoustic modes. They have low frequencies, and they interact. They call the, let me talk about the Brillouin scattering. Is it clear for everybody? Omega, so this is how it looks like. If you, yeah. You can see this is still like that elastic medium, right? But here, this becomes actually, if you come here, what is your, that the group velocity here? D omega over dk becomes 0, right? At the Brillouin zone border, your the group velocity becomes 0. Actually, this means actually that wave is getting reflected from the boundary. So we don't have to go. So this is your first Brillouin zone, right? So this is your second brilliant zone. So we never talk about anything beyond first brilliant zone. Everything we can explain from this one. If you won't consider this one, you can actually fold it back to the first brilliant zone. This is called zone folding. So you don't have to worry about anything about here. That is corresponding to actually this value. This is subtracting G vector. So if you do that one, this point is same as this point. This point is same as this point. So you can always bring back. So please remember, these are the brilliant zone. Remember, brilliant zone means what? The Wigner size cell of the reciprocal space, right? That's all. So, yeah, these are your K vectors, right? If you take this one, intersect here, you get the brilliant zone. No, this is 2 pi over, but this is the brilliant zone. The separation between the width of the brilliant zone is 2 pi over A. Pi over A minus. Okay, so if somebody wants, I just wrote down this one to do only considering nearest neighbor rather than doing that infinite number. So only if I have US, also I wrote as a negative number. Previously I wrote this one minus this one, that's why I had the positive. Here I wrote like this one minus this one, then you have opposite direction first, right? So this is US, S plus 1, S minus 1, only the nearest neighbors, just for you to understand. Again, you just plug in your solutions, you get that same. Just to, but remember, previous one we just did all the summations, then we approximated, right? But you can start only considering only the nearest neighbor. Just to understand how to do that kind of thing. So this is what I was trying to say. Anything more than this is a 2K maximum. Anything above this one is same as your that. What you have in the first brilliant zone, just to show it. Okay, so Vg is 0 at zone boundaries, right? If you take d omega over dk, when you take the derivative, this becomes cosine, Ka cosine 90 becomes 0. Okay, so yeah, give me a few more minutes. Actually, people have measured this frequency as a function of omega. Sorry, K, that's the wavelength, right? So everyone remember that our symmetry points from gamma is your center, so then you have X points to one of these surfaces. So this is some FCC. That is, right? So if you look at these are K, right? Along this one you can change your K vector. So if you go from here to here, this is a brilliant zone boundary, right? Here this is actually coming to the reciprocal scale. This is X point is your brilliant zone. You can say this is becoming perpendicular to that one. But if you look at this aluminum 1, 0, 0 direction. Remember, we talk about directions, right? 1, 0, 0 means in this case, this 2, 0 directions, they are pretty much same, right? They are degenerate. So that means you will only see one longitudinal and one transverse waves. You will see one longitudinal one transverse one. But if you go to 1, 1, 0 direction, that means they are two different directions. In that case, you will see one longitudinal and two transverse ones. Because in 3 dimension, you should expect to have 3 modes, right? But also it depends on what direction. So again, this is your zone boundary here. So, yeah. I will stop here. Yeah. Then next one I will talk about what happens if you have in this chain, you have two different atoms, M1 and M2. Previously, they all were same, right? In this case, you have Something called the optical modes also come in. Then you need to understand longitudinal, then acoustic, optical, transverse, longitudinal. I will explain all these things. Okay, I'll stop here. So please take your time and finish your homeworks by next Thursday. All the homeworks.
Thank you.
Then I will give you the solutions for each homework for you to compare your results. So today you have stat math exam?
Yes.
Okay.
You actually heard my friend? Yeah, she told she announced you it twice as Chandra Nepal. Chandra Nepal? Yeah. Then I didn't come. I don't know, nobody came. Yeah, maybe he was taken to promotion.
Thank you.
Taking good rate.
Yes,
Thank you.
But yeah, I mean, she Chandra, first time Chandra Nepal, it's like Nepal. Second time she was like Chandra Nepal. She said Chandra Nepal. No, she said Chandra Nepal. Then she said Nepal, like Nepal, Chandra Nepal. No one came. So now we know this. So after getting the permit, you have to wait there for a long time, right?
Yes. So I have just scheduled 12:30
Today?